Hi everyone, my name is Dimitrios Myrisiotis, and I will present Total Variation Distance meets Probabilistic Inference. My co-authors are Arnab Bhattacharyya, Sutanu Gayen, Kuldeep S. Meel, A. Pavan, and N. V. Vinodchandran. Our main result in this paper is a novel reduction from the estimation of total variation distance to probabilistic inference. In this paper, we are going to consider distributions that are described by basenets. What is a basenet? It is a DAG and a collection of conditional probability distributions that offer a succinct way of representing some high-dimensional joint distribution. For example, in this graph, there is a basenet over the variables x1 through x5. Let us consider a Boolean basenet, where each node may take the value 0 or 1. One way of describing the joint distribution that is represented by G is to use a lookup table that consists of 31 numbers. However, there is a description of G that describes the DAG and the conditional probability distributions that uses only 10 numbers. The distributions of x1 and x5 can be described by one number, because we know that the sum of the probabilities of the possible values that x1 can assume, for example, must sum to 1. So we only need to describe one of these values. Similarly, two numbers are enough for each of the conditional distributions of x2 and x4, and four numbers are enough for the distribution of x3. This gives 10 numbers. There are many notions of distance between distributions, but we are going to focus on TV distance. TV distance is defined as the maximum possible difference that two distributions P and Q can assign on any event A. This makes this kind of distance natural. Moreover, it has some other desirable properties as well. It is a metric, it is bounded, and it is invariant with respect to bijections. Now let us see what kind of notion of probabilistic inference we use. The notion that we use is as follows. Given some random variables, x1 through xn, and sets s1 through sn, such that si is a subset of the range of xi, compute the following cylinder probability, where x1 is in s1 through xn is in sn. Let us see some related papers. Goldreich, Sahai, and Vadan showed that it is hard to additively estimate TV distance for distributions sampleable by Boolean circuits. Bhattacharyya, Gayen, Meel, and Vinodchandran designed efficient algorithms for estimating TV distance between distributions that are efficiently computable and sampleable. Here, computable means that the PMF of the distribution is computable. In our previous work in ICML 2023, we proved that exact computation of TV distance between product distributions is RP-hard. We also gave FP tasks for estimating TV distance between distributions P and Q, where P is an arbitrary product distribution and Q has a bounded number of distinct marginals. In a recent work, Feng, Guo, Zerum, and Wang designed an FPRAS for multiplicatively estimating the distance between any two product distributions. Subsequently, Feng, Liu, and Liu gave an FP for the same task. Let us now see our results. We prove that for any class of baselets for which there is an efficient probabilistic inference algorithm, there is an FPRAS for estimating TV distance between any two basenets from C. One important thing to consider here is that the basenets that we are comparing are over the same DAG, which means that they have the same structure. As a corollary, we get that there is an FPRAS for estimating TV distance between any two basenets that they have small tree width, and they are defined over the same DAG. Small tree width here means logarithmic on the number of nodes, and this corollary follows by using our previous theorem with the folklore fact that probabilistic inference is efficient for basenets that they have small tree width. Our techniques are as follows. We use the notion of coupling from probability theory. Given two distributions P and Q, a coupling between these two distributions is a joint distribution xy, such that x follows P and y follows Q. We say that the coupling is optimal if it is a coupling, and moreover, the probability that x equals y equals w is equal to the minimum of P of w and Q of w. There is a nice way of characterizing TV distance by couplings. In particular, for two distributions P and Q, and random variables x and y such that x follows P and y follows Q, the TV distance between P and Q is equal to the probability that x is different than y when this probability is considered under the optimal coupling. There is an issue, however. Although there is this nice characterization, it is not clear how to find this optimal oracle. Sorry, this optimal coupling. What we are doing here is that we circumvent this issue by using partial couplings. Let us now see what is a partial coupling. A partial coupling L between distributions P and Q is a joint distribution xy, such that x follows P and the probability that x equals y equals w is the minimum of P of w and Q of w. As you can see, we do not require that y follows q. What we are doing is that we found some efficiently computable function f and efficiently sampleable distribution pi, such that the expectation of f under pi is equal to this ratio of probabilities, where in the numerator there is the probability that x is different than y1 under an optimal coupling O, where x follows p and y1 follows q. And in the denominator, there is the probability that x is different than y2 under the partial coupling L. We set z to be equal to this probability in the denominator, and the numerator is equal to the TV distance between P and Q. Let us now see how we can use this. If we estimate this expected value by a Monte Carlo approach and multiply it by the efficiently computable z, we get an estimate of TV distance. This is the high level of our approach. But something is missing. We need to also mention how we are using this assumed probabilistic inference algorithm. We use it in the computation of Z and in order to sample from pi. Let us now see two open problems. For what other classes of probabilistic models are there TV distance approximation schemes? For example, what can we say about undirected probabilistic graphical models? Moreover, we can consider other notions of distance or similarity. This is a QR code to download our paper from the archive. Thank you very much.